Hey, Chem 3276. I just wanted to give you a preview of the experiment that you're going to be doing on Monday. Here's the worksheet that you're going to be working with. And what you're going to be doing is basically trying to come up with um, kinetic parameters, specifically the Km and Vmax of lactate dehydrogenase. So whenever you arrive in lab, I will give you, or you will be given an aliquot, a protein extract that is believed to have lactate dehydrogenase. And the first thing that you need to do is you need to figure out basically what is the optimal amount of enzyme to use for these trials. So part one sets up part two. So if we scroll down a little bit, you'll see the exact amount of your CAPS buffer, lactate, and NAD plus that you will be adding to your cuvette. The last thing that you're going to add is the enzyme, okay, or the enzyme extract that I'm going to provide you with. So you'll be doing a total of 4 trials. The first one will consist of 150 microliters of lactate, 150 microliters of NAD plus, 15 microliters of the enzyme. So if you add that up, that adds up to 315 microliters. What you need to do is add CAPS buffer to get to the total of 1,000 microliters. So that would be 1,000 minus 315 would be 685 microliters. So you have to add 685 microliters of the CAPS buffer. Now, what I've provided at the bottom here, what I've just highlighted is 650 microliters of CAPS buffer. That is the appropriate amount of CAPS buffer for this fourth and final trial, where you're adding 50 microliters of the enzyme, 150 of lactate, 150 of NAD plus. Now, when you're going through this, you're going to do one trial with 15 microliters of the enzyme. You're going to collect data points, or you're going to read the absorbance at 340 nanometers at 0 seconds, 15, 30, 45, 60, 75, 90, 105, and 120 microliters. You will then calculate the delta A340 per minute. So the change in absorbance at 340 nanometers per minute. You will use that, the Lambert-Beer equation, as well as the concentration of, or sorry, as well as the volume of your overall mixture, which is 1,000 microliters or 1 milliliter, in order to determine the units of enzyme activity or micromole per minute. You're going to use that then to come up with a ratio of the level of activity per unit volume. So what I mean for this very last column, it's going to be this second to last column divided by the volume of the enzyme. So 15 microliters will be the very first one. 30 microliters will be the second, 40 microliters will be the third, and 50 microliters will be the fourth. So whatever you get in the second to last column, you'll divide that by the corresponding enzyme volume for that row. Okay, what you are looking for is you are looking for the highest number to come from one of these 4 trials. So what that means is we're kind of looking at it like best bang for your buck. What gives you the most amount of enzyme activity from the smallest volume? Whenever we find that, then we can say, okay, we'll proceed with every trial only having 30 microliters of that enzyme as an example. Okay, so like I said, you're trying to identify what is the most efficient enzyme volume, 15, 30, 40, or 50 microliters of your enzyme is, or what should you use in part 2? Now, as I scroll down, I wanted to point out for part 1, there's no graph that's required to be made for this table. You're simply looking for the highest value of that last column, this micromole per minute per volume. Now, part 2, you're trying to determine your kinetic parameters, your Km and your Vmax of NAD plus. Because one thing that's important to remember is that NAD plus is one substrate. So lactate dehydrogenase has an affinity for NAD plus. So it has a Km for NAD plus. Another substrate is our lactate. Well, Lactate dehydrogenase has a different affinity for lactate than it does for NAD+. So we are going to be targeting and focusing in on NAD+. Now, with that in mind, so for part 2, what you're going to be doing is you're going to be setting up a series of trials. You're going to do a grand total of 6 trials. Now, from part 1, you determine the enzyme volume that you use, whether that's 15, 30, 40, or 50 microliters of your enzyme. That is going to be the exact same amount from trials 1 through 6. Now, what is going to be different is your NAD plus volume. That NAD plus volume is going to be gradually increasing because what we're doing is we're varying the amount of our substrate, that substrate being NAD plus. Our other substrate, lactate, which I misspelled as lactate, lactate is going to be at a fixed volume. So it's going to be at a fixed concentration. It's going to be 150 micromole or 150 microliters. We're varying NAD plus, which is fine because we're determining the Km for NAD plus, or the Km that lactate dehydrogenase has for NAD plus. The CAPS volume, simply by the enzyme volume and the NAD plus volume varying, the CAPS volume is going to vary. Now, what that means is, let's play a hypothetical here. So let's say hypothetically that we have, let's say 30 microliters of our enzyme. That's the amount that we're going to use. What is the CAPS volume that we would then need? Well, for trial number 1, our CAPS volume is going to be our CAPS volume is going to be 1,000 microliters minus 150, minus 25, minus 30. So that would put us at 150 plus 25 plus 30 would be 205 microliters. So for this trial right here, trial number 1, the CAPS volume would need something in the area of 795 microliters of CAPS. Okay. Now, if you then track, well, oopsies, trial number 2. Well, again, the enzyme volume is going to be fixed. Our CAPS volume, on the other hand, well, that's going to change. That's going to drop by 25 because our NAD plus volume went up. So that would mean we're at 170 microliters. Okay. So you're going to have to adjust those volumes based on what you get from part 1. Now, with that all in mind, what you're going to be doing is you're going to be measuring absorbance at 340, at 0 seconds, 60 seconds, and 120 seconds. You're going to then get your absorbance, your change in A340 per minute. That will give you your enzyme activity. What you're going to be able to do with that is you're going to be able to develop a Lineweaver-Burke and a Michaelis-Menten plot. I mean, the Michaelis-Menten plot is the first thing that you're going to want to do. Your Michaelis-Menten plot is going to be, here's a crude representation of it, your NAD plus concentration, and on the y-axis, it's going to be velocity. So generation of our product per unit time. So you would want to convert that delta A340 into micromole per minute. So that's not on here, but I want you to do that as part of your calculation and generation of this graph. Now, with that in mind, this NAD plus right here, you're going to be given in lab the concentration of your NAD plus stock solution. So you're going to have to do a C1V1 equals C2V2 calculation to determine the concentration of NAD plus for all of these trials. All right, so what you're tasked with is part 1, determining the optimal amount of your enzyme to use for every subsequent trial in part 2. In part 2, what you're going to be tasked with and what you're responsible for is determining and measuring the change in A340, so the amount of our NADH that is produced in a given time frame. All right, well, I think that wraps things up. If you have any questions about this, I should be in the lab to stop by and talk to y'all. I'll also be talking about the Bradford assay. But at any rate, I hope you have a good one.